Morning, everybody. Let's go ahead and do our warm-up real quick. So today, a couple word problems involving graphing linear inequalities or equations. So number one, name the x and y intercepts for this linear equation given, 6x minus 2y equals 12. Use the intercepts of the graph, or the intercepts to graph it, and then figure out if it's increasing or decreasing kind of stuff. So let's take a look at that real quick. All right, here's your equation. Intercepts. How do you find an intercept? If you want to find an x-intercept, guys, how do you do that? Anybody? It'll be on your test. How would you, if I asked you to find an x-intercept, how would you go about doing that? I like taking out the 2y, because if you have an x-intercept, think about a graph, you know, where if it crosses the x-axis, I mean, you got to think about it. You got to understand like where these things are coming from. What do you know about this point right here? The y is 0. That's your guide. Like, it makes sense. If I think about a graph, y is 0. So yes, y would be 0. And when you plug in 0 for y, this basically goes away, the 2y, correct? So that's kind of what you were saying, I think. So we're left with 6x equals 12. So dividing by 6, x would be 2. So the coordinate 2, 0 is where this graph is going to cross the axis. In a similar way, if you wanted to find a y-intercept, you would think on the graph that means that x is 0. So you go back to your equation and you plug in 0 for x. And if you did, 6 times 0 would be nothing. And we'd be left with negative 2y equals 12. And dividing by negative 2, you'd get that y would be negative 6. So there's another point, 0, comma, negative 6. And now you got both intercepts, so you can graph it. That's all you need to graph a line, 2 points, 2, 0. So 2 over, 0 up, there's a spot. 0, negative 6. So 0 over and 6 down, 1, 2, 3, 4, 5, 6. Something like this, and then just draw a nice little line through them, and life is good. Very easy to do if you look for the intercepts, because you just basically plug it in 0 for something. If you plug 0 for something, it usually collapses down to something very easy to solve, and then you just plot your points and you're done. Use the intercepts to graph it, check, and describe whether it's increasing or decreasing. What does it look like? Increasing, write it down, yeah, and that's pretty much it. Moving on to number 2. Number 2, during the winter, a horse requires about 36 liters of water. Okay, so every horse requires 36. So if I have 1 horse, I'm going to need 1 36. If I have 2 horses, I'm going to need 2 36s, right? If I have H horses, then I'm going to need whatever 36 times H is for the horses. In a similar fashion, they say the sheep require 3.6 liters for a sheep. So if I have S sheep, and 3.6 times S would represent how much it's going to take to water the sheep. And of course, you have these two animals together, so you add them together, and this represents the total amount of water that these animals are going to be consuming. The farmer says he's able to supply all these animals with 300 liters. So at the most, the amount that they need, right, can't be more than 300. They got to be less than 300. They can have 200. Sure, that's fine. The farmer can give 200. They can give 100, but they can't give anything more than 300. So anything less than or equal to 300. So here's my setup. And let's go ahead and make a graph of this thing. You could solve for one in terms of the other, but I think we should use intercepts again. That was a pretty handy little thing. Doesn't really matter which one you make which, because it's just 2 different animals, and they don't depend on each other at all. What do you want to make this one, H or S? Okay, this one's S. S and H. So we're graphing the number of sheep versus the number of horses, or whatever it happens to be. Well, let's do intercepts again. So if I want to find the S-intercept, where it crosses the S-axis right here, then H would be 0, right? So let's plug in 0 for H, find out where it crosses this S-axis. We'll call it the S-intercept. In this case, H would be 0, and plugging that into my inequality, basically that's 0 then. So you're really trying to figure out when 3.6s is about equal to 300. So divide both sides by 3.6, get your calculator out and type that in. I'll try to do it in my head, but no promises. 5, 6. 83.3 repeating? Okay, so this is going to cross up here at 83.3 repeating. That is my S-intercept. Okay. I need another point. Might as well find the H-intercept, or is it across this axis? So in a similar fashion, if I'm trying to find the H-intercept in this graph, S would be 0. And if you plug 0 in for S, then this equation turns into 36H is less than or equal to 300. And we're not going to really worry about the inequality. We're trying to figure out what it equals to. Divide 300 by 36, and you should get 8.3 repeating, I believe. Always check my mental math. I'm never 100% confident up here. Cool. So I got 2 points. And it's an inequality, so I got to worry about solid or dashed lines. Solid or dashed based on less than or equal to. Solid, yeah. So we're going to just draw a solid line between these two dudes. And I think since we want these things to be less than 300, we're probably going to be shading below. So less than is a big term right there. So anything in there should work. The animal should be able to get their water, and that's a sweet deal right there. And that's basically the whole entire warm-up. Let's do some learning goals and get ourselves ready to learn some special functions today. They're special. Students will learn about special functions, including piecewise functions, step functions, and absolute value functions. Sure. What were we talking about with the endpoints?
I remember last year you had to actually label where the function ended and started, on the graph. Yeah.
You got your open and closed circles and stuff?
Yeah.
That's all I care about. I think you're okay.
Well, I have a question on one of them that I said I don't know how to do this weird.
Okay.
It's I wanted to make sure I had one of the functions correct, and I graphed it, and then the graph shows nothing. I'm not sure why. It was -2 to the x. Remember I went and graphed that, nothing showed up. I tried on 2 separate graphing calculator engines.
And you divided by your.
No, that was just a graph of just the thing to see what it looked
Just
like.
2 to the x?
Yeah, just, -2 to the x.
Nothing?
Yeah, that's what I thought would happen, but
yeah.
Nothing showed up on either one of them.
Okay.
It's really weird.
We'll look at it. That is weird.
Because I tried it on the online Decimos one and on my 89. Both of them showed up with nothing.
Okay. We'll look. Notes. Lots of notes today. Let's get going. Today's not going to be crazy hard. I don't know, because it might be hard because it's new to you, but we'll find out. So homework 1.5 is due today. Homework 1.6 over what we're about to talk about, normal 2-day thing. That'll be due on Monday. Monday, we're back to school, so full time for everybody except for maybe the few remote students who might still be out there. That's exciting. Did you hear about that? Oh, yeah, that's great. I'm pumped for that. So cool. All right, let's get to the notes. This is section 1.6. It involves special functions. Found on page 47 of your textbook. Nice short title for you today. Special functions. So these are functions that come up once in a while. They're not going to probably be the heart and soul of this course, but they're just good to be exposed to them because they do come up once in a while, so you need to know about them. All right, here we go. First things first. Something called a piecewise defined function, or just piecewise function. Here's the definition of it. A piecewise function is a function that's defined in different pieces. It's not one equation that describes everything from negative infinity to infinity. Maybe there's an equation that describes it where x is between -1 and 2. Maybe there's another piece where it describes it from x is 2 to 7 or something like that. But it's defined in different pieces, hence the term piecewise function. The notation here, they're going to say f of x equals with a bracket, and each piece inside this bracket will have its own line. So they'll say, okay, here's an equation, like equation number 1, And they'll tell you a condition. They'll tell you when that piece exists on your graph for what x is. X is more than 1, or x is between 4 and 5, or something like that. They could have another equation, another piece, equation 2, same thing. This equation is defined for this condition where x is between this and that or something. And you can have as many pieces as you want. It can go down, you can have 20 pieces, you can have 30 pieces. They're not going to do that to you. You're probably going to have like 1 or 2 or 3 pieces maybe max. But you could have as many as you want. Won't make too much sense till we do an example, but that's the clear idea. Down at the bottom, please make sure you note to yourself that, we got brackets and parentheses, and all that stuff, Brackets means it is included, correct? Graphically, a bracket will be represented by a closed dot. So a dot circled in will mean, yes, I include this point. It means the same thing as a bracket. Bracket is when we're writing it out. From x goes from here to there. On a graph, we need some way to say I include it or I don't include it. On a graph, a point that is circled and completely filled in means it's included on that piece. If you have an open circle, then that means it's not included. So think of the closed circle as your bracket and think of your open circle as your parenthesis. Takes a little getting used to graph a piecewise just because it's different. You haven't probably done it before. But it's really not that complicated. The pieces themselves will be easy to graph. You just got to remember to only draw them where the condition is met. So let's take a look at some examples because this is too much theory. What's he talking about? Here's a good example of a piecewise function. So example number 1, they say f of x is this. They got the brackets. That means it's piecewise. And up top here is your first equation, your first piece. It's going to look like a graph of x minus 3, but you're only going to draw it where x is less than or equal to 1. As a separate piece, you got f of x is 2x. So it's going to look like a graph of 2x when x is more than 1. Now, I'm not going to do all this nonsense, but let's just talk about it on the board. So, yes, let's write down this example. F of x equals, let's actually do it. You guys just practice and do it. X minus 3 when x is less than or equal to 1. And they wrote the word if. You don't have to write the word if. Equation condition. That's basically all this comes down to. Equation condition. Equation condition. All right. How do you go about doing this? Well, for a minute, I think when you're first starting off, even when you get kind of good at this stuff, it's probably good for a moment just to not even worry about the fact that there are different pieces. Don't worry about all this nonsense for a second. X minus 3. Can you just graph x minus 3? I hope so, because it's a line, right? That was yesterday's lesson in Algebra 1. So the y-intercept what? At -3, correct? So this piece will cross down here at -3. And the slope is a 1, right? So it's going to go over 1, up 1, over 1, up 1. So another point would be maybe here, over 1, up 1, maybe there. And if I did draw all this, it would look something like that. Do we all agree that's kind of a reasonable graph of x minus 3? Okay. Now, I encourage you to draw the whole thing at first because you're comfortable with that, right? Here's x minus 3, okay? But look at the condition. This graph only exists when x is less than or equal to 1. So you only want the part drawn where x is less than or equal to 1. I only want it from here over. Are we okay with that? So erase this part because I was just drawing that to just get a feel for what this piece would look like. It's only going to go to right here where x is equal to 1. Now here's where the closed and open dots come from. Can on this piece, look at this piece right here, look at the equation. Can it equal 1? Yes. So bracket or parenthesis, what would you normally say if it can equal it? Bracket, right. And on the graph, bracket means what? What was that thing? Close or open dot? Close, right. So right here, I'm going to draw a little purposely a little point right there that says, yes, this piece includes where x is 1. So you see what I'm doing? I'm just drawing this thing like normal. And I'm erasing where it doesn't exist. It only exists for x less than or equal to 1. So I'm going to include that and erase the rest. And same with the next piece. The next piece looks like 2x. So before I get all, erase happy, what's 2x look like? Well, there's a plus 0 here, correct? So really the intercept is 0. So I'm thinking in my mind, and the slope is 2, correct? So I'm thinking every time I go over 1, I'm going to go up 2. So it's going to start here, and that's going to go up 2 here, correct? I'm going to go over another 1. It's going to go up another 2. And it's going to look like that, basically, correct? Now, do I want to draw the whole line? No, just where x is more than 1. So where's x1? Right here, correct? And up here, so I want to erase this part over here. I don't want anything over here. I just want where x is more than 1. So it's going to look like this kind of thing. Now this piece, you always want to worry about the ends. Do I need an open dot or a closed dot? On this piece, can x actually equal 1 on this piece? No, it cannot. So in this piece, you draw an open circle. This piece includes, the bottom one included -1. Excuse me, included 1. So I drew a circle in. This piece here did not include 1. Are we okay with the circles? Why they are?
Will it still be dotted because it's not equal to?
Well, the one, you mean the dash or you mean the open circle thing? The dash I was just doing because I didn't want to erase too much or something like that. I should have probably done that, right? Probably confused you. Probably thought it was an inequality or something like that. But it's still filled in. These are always going to be filled in, okay? So there's no dash lines or anything like that. Only thing you got to worry about is open and closed circles. That's it on this stuff. But that's it for this piece. So that's kind of what this thing looks like in 2 different pieces, and that's hence why we call it a piecewise function. Let's see if we can do another example. That was a good one. That looks like a lot of work. I'm not going to do that. I'll make one up. Let's make up one. So how about this? Second example. F of x equals, here we go, -x when x is less than -1, 5 when x equals -1, and 2x plus 3 when x is greater than or, just greater than -1. So it's got 3 pieces. It's all right. We will just go through them all one at a time, graph them, and see what they look like. Okay, so I'm going to do a dash line, not because it's dash, but because I just don't want to erase too much. One piece at a time. -x. Got a plus 0 on the end, right? So again, goes through the origin. You would think, correct? Go through the origin. And the slope is negative, right? So over 1, down 1, over 1, down 1, etc. What's up? Okay.
I'm sorry, I thought it was you, but I can't tell it. I'm sorry.
Oh, you're good. Thank you, Sue. There you guys go. So crosses the origin, right? Slope is -1, so if I go over 1, I should go down 1. And if I connect them, you can just kind of see in your mind there's going to be a graph right here, correct? Okay. Now, I'm just going to do a dash line. Where's this piece defined, though? It goes forever, correct? But this piece is only defined when x is less than -1. Where's -1, right? There, correct? So I only want to draw it over here where x's are less than it. So I'm not going to be having all this stuff over here. That was just as a reference. You might want to draw a little reference. Okay, I know what the whole thing looks like, and then erase it. So it's going to look like this. This piece where x is less than -1. Should you have an open circle or a closed circle on this piece? Open, yes, exactly. So open little circle right there, and then we're kind of done with that piece. On to the next piece. By the way, can you figure out what y value that would be at right there? How would you figure that out? Well, x is -1, right? And even though this piece, it doesn't include -1, if you plug it in, what's -1? It's +1, right? So you do know that it would be here at 1 if it existed, but it doesn't, right? But at least you have a reference. Okay, now, at -1. This doesn't say greater than, doesn't say less than, it just says at -1. You get out 5. So it's a lone point. 2, 3, 4, 5. Here's 5. When I plug in -1, I get out just as a single point of 5. Not a range of numbers, not a whole line or anything like that, just a lone point right there. And lastly, we have this piece, 2x plus 3. What would a graph of that look like? Well, y-intercept's 3, correct? Slope is 2. So if I start up here at 3 and was to go 1 over 2 up, 1 more over 2 up or something like that, it would kind of look like this right here. Fair enough? Okay. Now, where do you want to draw this piece? Only for x's more than -1. So do I need anything over here? No, I don't. Here's where x's would be less than -1. We don't want that. We just want this. So this piece kind of looks like that right there. And where is it? Does it link up with this other piece? Sometimes it does. Sometimes it doesn't. Depends. I don't know. Let's check. This piece starts at -1, correct? If you plug -1 in, what would you get? 2 times -1 is -2, plus 3 would be 1. So that's the same y value as this one, isn't it? So they do hook up right here. But does this piece have an open or closed circle where they hook up? Still open. So this is still an open thing right here. And this is kind of what this graph would look like, a V thingy, where this point doesn't exist, but then all of a sudden it pops up there. So it takes a little getting used to. I think you get the gist, right? Just draw each piece individually. That's what I strongly encourage you to do. Don't even worry about all of them. Just draw one at a time. Draw the whole thing if you need to, okay? And then just erase the part that doesn't apply. So if they just say x is less than -1, keep the part where x is less than -1, erase the rest. And that's basically all there is to graphing piecewise. Feel okay? Yes? No? I'm getting a vibe like no. Do another one? Let's do another one. Okay. Let's go one more time. Let's try this. F of x equals 4 when x is less than 2. It is x when x is between 2 and 4. And it's going to be a graph of 10 when x is greater than or equal to 4. All right. Let's just go nice and slow. So one piece at a time. Graph is 4. That means it's always 4. It's 4 here, 4 there, 4 there. It's just going to be a nice straight line of 4. So this piece, this is kind of what a graph of just y equals 4 looks like. We okay on that? Now, of course, you don't want to draw the whole thing. I'm just drawing that as your starting point. You only want this thing to be drawn for x's that are less than 2. So you go to where 2 is, and you're only going to have it the part where x is less than 2. So this part right here is what I'm going to draw. The rest of this, I was just doing to get a feel for it. Are we okay on that so far? Okay. Now, right here, open or closed circle, look at the piece. Do I include 2 or not? No. So open circle? Yes. So open circle right here. And this is the first piece drawn. I start all over again. Forget the first piece, it never even happened. Second piece is just x, right? What's a graph of x look like? Well, it's just a boring graph that goes right through the origin right here. Here's the whole graph of x. Cool? I only want this graph. I want to erase all parts and keep the parts where x is between 2 and 4. So if x was 2, let's see. What would you get out if you plugged 2 into this piece? Because this is all we're working with right now. If x was 2, then you'd get out 2, correct? So when I plug in 2, I should get out 2 right here. Now, on this end right here, compared to the 2, equal sign, right? So guess what? It's going to be a closed circle right there. And I'm going to keep drawing this until I get to where? Until x gets up to 4. So here's x is 1, 2, 3, 4. So it's going to go all the way up to about here-ish. Here, x is between 2 and 4, correct? But notice on this piece, when you get to 4, it's not less than or equal to, it's just less than, right? So on this side of my piece, I don't need a closed circle. I need a open circle right there. So this is that piece for the middle. It's just a graph of x. I don't need this. This was just here to kind of give me a guide. But here's a graph of x. It's just only existing between 2 and 4, including 2, closed circle, excluding 4, open circle. Make sense? And the last piece is just a graph of 10. So just like the graph of 4, it's just going to be a boring straight line, only up at 10. So let's see, where's 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like this. Way up here, there's going to be this graph of 10. Imagine it goes all the way. That's what a graph of 10 would look like. But the piece I only care about is drawing it only when x's are more than or equal to 4. So here's 4 on. Notice I did a closed circle there because x can be 4 on this piece. And that's about it. So it takes patience. That's all it does. It takes patience. Don't look at it and try to do the whole thing at once. Do it in pieces. Draw just a graph of 4. Erase the part that doesn't apply. Oh, do a graph of x. Okay, erase the part that doesn't apply. Do a graph of 10. Okay, erase the part that doesn't apply. And that's basically all there is to piecewise. All right, I think I've harped on that enough. Let's go ahead and get back to stuff now. So the second function today, there's 3 of them, is called your greatest integer function. Sometimes it's called a step function. You don't have to write all this nonsense down. Just the box at the bottom. That's all I want you to harp on. I don't usually say greatest integer. They also call it a floor function. Inside those parentheses are a whole bunch of things that they might refer to it as. So your calculator, for example, will say int of x. So if you're trying to find this function in your calculator, you might want to make a note to yourself right now. Int of x is the thing you're going to look for in your calculator to graph this thing. Your calculator won't say floor. I might just say that word, floor. So they also have some mathematical notation. They might have an x with a double bar. That's what you're going to see in Reveal quite a bit. Or they might have x in these bars where just the bottom is kind of got little hooks to it, like a floor, like towards the bottom or something like that. It's basically a fancy function, a fancy term for rounding down, basically. This is a rounding down function. You round down to the integer less than you. So if I said 6.9, you get out 6. If I said 20.9, 20. If I said 0.36, 0. Basically, you throw away the decimals. Basically, you round down. One thing you got to worry about, though, is what's rounding down for a negative number mean? Because if I say like negative 7.2, people think 7.2, I'll round to 7 because that's what's down. But when I mean round down, I mean round to the left on the number line. So negative 7.2 would be negative 8. Yeah, you got to go that way. So worry about those negatives. That's the only thing you got to really be scared about. We'll do some basic examples. So just round down. That's all this means. Round down. Round down. And down means to the left, basically. Okay, so on the board, got a bunch of examples. Nothing too complicated. Humor me, 6.9 rounded down would be 6. So this function would give you out 6. 13.21 rounded down would be 13. like I've just been harping on with the negatives, make sure you're going that way on the number line. If you're at negative 7 point, visually what's going on, here's negative 8, here's negative 7. Dang it. There's negative 7.45. And by rounding down, I mean going to the left, right? So don't confuse yourself. Common mistake. You're going to think it's going to be negative 7. It's not. It's negative 8. Rounding that way to the left on the number line. And negative 228.96 rounded down. What do you think that's going to be? Negative 229. Even more over there. That's really all you got to know about what it means. It's just a fancy one of rounding down. Now, well, what's the graph that's going to look like? Let's graph this floor function. So I'm going to plug in a number, and we're going to tell me what the floor is coming out, okay? Any number between 0 and 1. Pick any number at all. What do you get out? Pick a number between 0 and 1. Think of a number between 0 and 1.
0.1.
Thank you, James. What's 0.1 rounded down? Okay, pick another number. Don't make James do the work. 0.8. 0.8 rounded down. What do you get? Okay, so no matter what you plug in between 0 and 1, what do you get out? 0. Okay, so this, until I get to 1, just gives me out 0. Now, what happens when I actually give you 1? Round 1 down, what do you get? 1, right? So when you get to 1, it actually jumps up to a new piece. And then if I give you anything between 1 and 2, what are you going to tell me the answer is? 1, right? So you're going to have a nice little thing that looks like this until you get to 2. And then at 2, it jumps up to 2. And this is kind of what a floor function will look like. You might want to kind of jot down roughly that this is what the basic graph of this thing looks like. And it keeps going up. It's just a staircase forever and ever and ever. Nice little staircase there. Isn't that cute? Now, graphing these, if they get really complicated, I mean, that one's not that bad. I'm just plugging in some number. But the examples do get kind of gross. And that's why I want you to use your graphing calculator on this kind of stuff. So I'm not going to do this one, but let's jump right to example 4 today. Okay, so write down example 4 from your textbook, because we're going to do this one. Now, they say to make a table. Let's not do that, okay? Let's just use our calculators to figure out what this thing's going to look like. So the first thing they say is let's write down the problem. F of x is the floor, or the greatest integer function, or whatever you want to happen to say. Why am I calling it floor, by the way? This thing rounds down, right? Rounds down towards the floor, kind of. That's why it's called floor. There's also one that's called ceiling. Guess what that one does? It rounds up, yeah. So that makes sense. But this one we're graphing 2x minus 1. So calculators out. Here we go. We're looking for the greatest integer of 2x minus 1. Let's practice some graphing. So first off, whenever you graph anything, you need to go to the y equals, correct? If you got something in there, clear it out. Clear. Now, where do you find this greatest integer function or anything like that? I said, and if you didn't write it down now. It's called int, I-N-T, okay? This calculator has so many things. Here, I'm going to tell you some gold now. Ready? You see down here at the 0 button above it in blue says catalog. So anything in blue, you always got to hit second first. Go hit second, and then go to 0, catalog. This has everything in your calculator there. So if you can't find something and you don't know what buttons to push, you can always go to catalog and find it. Now we need int, int. So you need to go all the way down to i's. Now I would not recommend scrolling. Instead, you can access all these things. They all have letters in them, don't they? The greens? Greens all got letters. So the greens you access by hitting the green button up here that says alpha. So hit alpha. And then find the I button. Where's the I button? It's right above the x squared. So hit the alpha and then the x squared button, and it'll take you. You might have to do it twice. I don't know why mine has to do that. it'll take you down to the i's, and then your scrolling is not going to be quite as long. Scroll down, and you finally should see something that says int. That will stand for your greatest integer function. So you hit enter, and it doesn't have the double bars, but it means the same thing, int of whatever. We, inside of our double bars for this example, is 2x minus 1. So type in 2x minus 1. And whenever you do a function like this, int, see how I had that parenthesis first? You got to close the parenthesis. So right above the 9 key is your close parenthesis thing. So it says, find the greatest integer of 2x minus 1. And that's pretty much all there's going to be to it. I would hit zoom and then 6 to reset things just real quick. Just a good habit I have. And when you see a graph, look at that. It's got all these little stairs, right? Just like I was talking about. If it's not clear to you exactly how much is going on, you might want to zoom in. You know, zoom. Number 2 says in. Maybe get a little closer to your staircase. Hit enter. If you get a better graph of what this thing looks like. And notice on your graphing calculator, does it graph the whole? Does it graph the ends? Does it graph the closed dots and the open dots? No, you need to know to do that on your own. Now, I'm totally okay with you kind of just copying your graph and writing it down. But notice the one I gave you originally. Where are the closed dots? On the left side of each piece, right? And the open dots are on the right side. Every time. I don't care how weird of a thing you're graphing. If you're graphing a greatest integer, that's always how it's going to be. So if I was given this problem, I would go copy this graph down the best I can. And on each piece, on the left, I would put a closed dot. And on the right, I'd put a open dot. And that's kind of all there is to a greatest integer function. This is very useful for practical applications in life, like, you know, you're only charged for every minute for a cell phone or something like that. You know, round down to the nearest minute and only charge you or something like that. So it's kind of useful. Honestly, I don't want to spend a lot of time on this because we're not going to use this all year long at all. This is probably the most useless thing I'll teach you so far. But you should be exposed to it, and it's a greatest integer function. Last function today is the absolute value function. This is important. This is something that will matter. Piecewise, comes up sometimes. Step function, greatest integer function, nah, very rarely. Absolute value functions, they come up a decent amount. This is probably the most useful thing I'm teaching you today. I'm sure you've seen this before, right? Absolute value of something. It just means to, basically, you're trying to figure out how far away from the origin you are. It's a distance thing. It makes things positive. So if you give you a positive number, 5, you take the absolute value of it, it just keeps it positive. It's already 5. No problem there. If I give you 29, the absolute value of 29 is just 29. Negative numbers, though, when you take the absolute value of them, they're negative. And this thing tells you the distance you are from the origin. So if you're at -7, how far away are you in length from the origin? You're 7 away from the origin. So the absolute value of -7 would give you +7. The absolute value of -80 would give you +80. So basically, it makes things positive. That's all this thing does, makes things positive. Technically, the absolute value function, and in your calculator, if you need to find it, it's ABS. If you go to catalog, it's the very first thing. That thing I just showed you, the second catalog thing, it's all alphabetical. And the very first thing on the top of your list is ABS, stands for absolute value. When we write equations, though, we write the x with the bar on both sides. But it's defined piecewise. It's defined in 2 pieces. There's a piece on the right side of the plane, and there's a piece on the left side of the plane. The little corner you see, and you should probably copy down that graph too at the top right. You know, this is what a graph of absolute value looks like. It looks like a V. The corner of the V has a name. It's called a vertex. And probably that's the #1 thing you need to find is like, where's the vertex? And the trick is the vertex happens at wherever is inside the absolute value, whatever's inside there, when it equals 0. So for this one, for example, you got absolute value of just x. What's inside the absolute value? X, right? So if you go set up an equation for that equaling 0, well, then that just means x is 0. And if you look at the vertex on that picture on the top right, the corner happens right where x is 0. It'll open up because it's going to give you positive numbers out. That's what absolute values do. They give you positives out. And the official equation is given them right there in the middle in 2 pieces. If x is greater than or equal to 0, you just graph whatever it was, x. So if they give you something greater than or equal to 0, like 7, it just gives you out 7. If it gives you something greater than or equal to 9, it gives you out 9. Makes sense. That's what absolute values do. The other piece, though, down there, if it's less than 0, it gives you out the negative of it. So if you had like -8, and that'd be on this piece on the bottom right, -8, because -8 is less than 0, right? And you plug that in there, you get -8 out, which would be +8. So nothing too tricky there. All right, let's look at an example. Example number 5 here. Let's go ahead and graph this thing. Let's not try to do it by hand. Let's actually cheat. Okay, once in a while, let's cheat. So you need to graph f of x is the absolute value of 3/4 x. 3/4 x plus 3. Now, I should teach you how to not cheat, too. I always told you the vertex, the corner, happens when the thing inside of it is equal to the magic number of 0. So if you go type what's inside this thing and set it equal to 0. The thing inside there's 3/4 x. If you set it equal to 0, divide by 3/4, you get x is 0. When you graph this thing, you will see the vertex at x equals 0. Let's practice graphing it. It looks like you're ahead of me on that, which is fine. So, yep, go back to your y equals, clear it out. Absolute value, there are buttons you can find it, but again, I would just always kind of go back to second catalog. It's got everything. You can't mess it up. That's the very first thing, so you don't have to scroll or do anything. Just hit enter. Some calculators will say ABS. Some will actually put the bars. Depends on which model you have, okay? Either way, inside the thing, you put whatever you're studying. 3/4, that just means 3 divided by 4, times x. That's what I'm graphing right here. You hit enter. And remember last time we zoomed in. You remember that? We zoomed in on the last example? So our window's kind of jacked up. So you might want to do that zoom 6 thing again. Zoom 6. Boom, there comes your V. It's your standard V thing. It's stretched a little bit. We're going to talk about stretches and shifts and stuff on Monday. But that's kind of the graph of it. Draw a rough sketch of it, and you're done. That's kind of all there is to absolute values right there. Let's try to do this one, okay? Graph f of x is absolute value of x minus 1 plus 3. Put your calculators down for a second. Let's try to do it by hand first. And then we'll come back and graph it and confirm that we actually did it right. Okay, here we go. So graph this one, and here's what we're going to do. The thing I keep harping on is the vertex happens when the inside of the stuff inside of this is equal to what? What number did I say 3 times? Should be equal to 0. It was in your notes when the stuff inside your absolute value, this is what's inside my absolute value, right? When it's equal to 0, that's where my vertex will be. So I'm trying to figure out where my vertex is. And that's pretty easy to solve. That happens when x is 1. So when x is 1, this is where my corner is going to be, okay? Now, where is it going to be y-wise? Let's go plug in 1. Let's figure it out. When you plug in 1, what do you get? 1 minus 1 is 0, right? The absolute value of 0 is 0. And 0 plus 3 is 3. So when I plug in 1, I should get out 3. There's my vertex. There's where my corner is going to be. So I bet the rest is going to go like this, some kind of V dealy. But I don't know. Let's not guess. Let's plug in another number. How about we plug in 2? Let's plug 2 into the stupid thing. If I plug 2 in, 2 minus 1 is 1, right? Absolute value of 1 is 1. 1 plus 3 is 4. So when I plug in 2, I will be getting out 4. So I know that this piece, this side of the V, will kind of look like this. Here's where the quarter is going to be. And it's just going to proceed up like this. On the other side, let's plug in something to the left of 1. How about 0? When you plug in 0, 0 minus 1 is -1. The absolute value of -1 is 1. And 1 plus 3 is, again, 4. So when I plug in 0, I'm also getting out 4. And here's the other piece. So by hand, that's kind of how I figure it out. First, I would figure out where the vertex is. And how do you do that when the inside of the stuff is equal to, say the number. Thank you. 0. Good. And then once I got where the vertex is, maybe I plot something to the left of it, maybe something to the right of it also, you know, and then figure out where that V is going to go, and then just draw your lines. Now let's graph it with our calculator and see if it actually looks like that. So let's do that. Y equals clear second catalog absolute value. Make sure everything goes where it's supposed to. The x minus 1 goes inside the bars, right? If you need to ever get out of a function, just hit the right key. It'll get you out. So now I'm outside of it. X minus 1 is inside the bars. I'm outside of it. And now I just need to hit plus 3. And then I might want to hit zoom and 6 just to double check that I'm looking in the normal place. And here it comes. Looks basically like ours, correct? Okay. So that's how you're going to graph an absolute value function. So we covered 3 today, and it was kind of cumbersome. Again, in your calculator, here's just your notes about where to find them. Second catalog, right? And the greatest integer function, the floor one, the one that rounds down, that's called int. And the one for absolute value is called ABS. I strongly encourage you for once to use your calculators very heavily on this section. Cool? All right. That's it for today. Homework 1.5 is due, and homework 1.6 over this is assigned and due on Monday. Monday, I will see everybody back at school. Good work.